Welcome back. In our first session together, we looked at the importance of developing machines that are sensitive to ethical considerations and capable of factoring those into their choices and actions. At the end of our class, we focused on the importance of emotions such as empathy and compassion, of somebody who has what we called a theory of mind, the capacity to know that what's in other people's minds differ from ours, and perhaps even empathetically deduce a little bit about what they are thinking about. We referred to these as suprarational faculties, beyond reason. But eventually we're going to need systems that are capable of learning, that are capable of subjecting their choices and actions to top-down principles, and that have various forms of input that go beyond reasoning alone. In section 1 of this course, Sheldon talked about the importance in human development of collaboration, cooperation, the ability to really work together and achieve a goal together. Now, this is partly learned, partly inculcated by the community, but also seems to be intrinsic to human nature. Consider a task such as getting a large piano up to the second floor. Wouldn't it be great if you had a robot assisting you in that activity? But if you've ever done that with another human, you realize the importance of your ongoing communication with each other, the importance of understanding what the other individual thinks you are doing. In effect, your ability to at least mildly read their minds. But it's not just this theory of mind which becomes an important capacity. Look at our sociability. The fact that cooperating with each other is fundamental for some of us, for most of us. It's not just that we know it's in other people's minds, but it's we understand the basic rules of our community, of our society, and therefore we understand what's appropriate, what's acceptable, and what may not be acceptable. And we can apply that in new and unique situations. With the onset of a pandemic, we all know that a simple handshake is no longer a simple action. So we actually have to feel out the other person whether a handshake or some other form of greeting is appropriate. The need for a hybrid moral machine confronts us with a simple problem. Who's going to be the model? By what standard shall we develop and evaluate our success when we have this engineering project? Is our model a sociopath or the average human being? Or should our model be a highly sensitive individual? Furthermore, regardless of the model we choose, does the moral machine have the capacity to deal with very difficult ethical challenges, some of which are wickedly difficult? Those of you who've taken a course in ethics have been confronted with various philosophical thought experiments. For example, what would you do if a train or a trolley car was coming down the tracks and it was about to kill 5 workers on those tracks, but you were standing by a switch and you could shift it so it did not kill the 5 workers? Unfortunately, though, there would be 1 person on that other track. Would you take responsibility for altering the course of that train in order to achieve the greatest good for the greatest number? There are hundreds of these thought experiments, and some of them have recently been applied to self-driving automobiles. So if the self-driving automobile confronted a situation where it would be forced to kill 5 civilians, or perhaps it could drive into a wall or off a bridge, saving the 5 civilians but killing the occupants in the car, should it do so if, for example, there was only 1 occupant in the car? Research on this problem has shown that the vast preponderance of people go with the utilitarian calculation, the greatest good for the greatest number. Unfortunately, the research also shows that if the car was going to kill the occupants of the car, people would not buy that car. They would not buy such a self-driving car. These are all the kinds of discussions we have to have in our society, but they raise the wickedly difficult challenges that might be posed on occasion for a moral machine, and the more wickedly difficult challenge for us and how we want to design these machines in terms of what values or choices they're going to bring in. Should the machine have the capacity to learn from its mistakes? Presumably you would want a machine to learn from its mistakes, but the more a machine learns, the more it's changing its own programming. And that, as it changes its programming, its choices may be less predictable, and it might do something unanticipated in a new context. We may want the machine to deal with radically new situations, but would we want it to deal with radically new situations if its capacity to do so made it less reliable in the way it handles some of the tasks for which we generally presume there is a right action? How would we want a moral machine to deal with a situation in which there were many other stakeholders and the stakeholders prioritize values very differently? Throughout the history of artificial intelligence, there have been periods when great progress is made and great expectations, and there are periods of stagnation. The founders of the field, during a meeting at Dartmouth College in 1956, they thought it was just a matter of a decade or so before they would have machines that could beat a grandmaster at chess or could communicate with natural language. They thought it would take a summer for a graduate student to design a machine with visual acuity that could identify the objects in its perception. As many of you know, it took more than 30-odd years before IBM's deep learning beat Garry Kasparov, a grandmaster at chess. We still don't have AI systems that have great accuracy in communication, though they are getting better. And we still do not have machines with high-level visual acuity able to distinguish the many objects in their fields. So we have seen these advances and we have seen slowdowns. Most of you will have noticed that there's been tremendous enthusiasm in the past few years coming out of progress made in a field known as machine learning. And this progress has particularly looked toward the advent of a new form of machine learning known as deep learning. Machine learning can come in many different forms. One of it is called reinforcement learning. So reinforcement learning is what we often do with a child, where we give a reward if they come up with the right answer, or at least the answer to what we think is most appropriate, or we met out some form of punishment if they do something inappropriate. And there are ways in which you can create a reward, or at least the illusion of a reward and a punishment for artificial intelligence based on whether they take more or less successful or more or less ethical courses of action. Deep learning is somewhat different. Deep learning is actually a revival of neural networks where we have greater power and more sophistication in the way we design these networks. And in effect, what the machine can do is look at a vast body of knowledge, sort through it, and discover salient relationships within that information and give those relationships as an output. The advent of deep learning has created great excitement, and it has created projects where nearly any conceivable database of information is being subjected to a process to look for relationships that might not have been perceived otherwise. And it led those in the AI community to believe that maybe for artificial intelligence is going to come much more quickly than we thought. And shouldn't we begin to think about the safety of advanced AI, the safety of artificial generally intelligent systems or artificially super intelligent systems, again, like the hero in the Spark Hunter file. The power of deep learning was expressed through examples of deep learning systems that were able to solve very quickly computer games, or it also became important in solving the game of Go. So many of you may know the game of Breakout. The company DeepMind was able to deploy a deep learning algorithm that not only could beat humans at the game of Breakout, but actually came upon strategies that only very advanced players of the game would have ever recognized. But along with this deep learning revolution in the development of AI systems, quickly there appeared a series of problems. The most important of these problems was algorithmic bias. Most of the databases that deep learning algorithms worked with, they were accumulated on past information and already had within them what you might consider existing human biases and prejudices. Some of these biases were racially specific. Others, for example, might be gender specific or might prejudice against those with disabilities. And a great deal of work now has gone into trying to understand algorithmic biases, because if the biases are inherent in the data coming in, those biases are also going to affect the output of the systems. So how do we eliminate those biases? And there's been a lot of work going on in AI ethics about whether we can perceive the biases in advance, whether we can eliminate those biases, or how biases should be factored into the eventual choices and actions that might be taken. But it's not just the algorithmic biases. It's a capacity for a learning system to potentially do something very destructive. There's been a campaign that has been ongoing over the last few years about enacting a treaty that puts restrictions on the deployment of lethal autonomous weapon systems. Lethal autonomous weapon systems are weapon systems that can select a target and destroy it with little or no human input. And many people believe that machines should not be making life and death decisions about humans, and therefore we need some treaty to restrict this. But what makes all of this more difficult is that a lethal autonomous weapon, it could be a complex adaptive system that in some situations acts in unpredictable ways. Or if it's a learning system, it might alter its actions in ways that those who had deployed the system had not anticipated. So for example, it might actually escalate existing hostilities, or it could even start a new war. So this is among the concerns that appear. There are issues around the conglomeration of data in the way in which these systems, these deep learning systems, can conglomerate data that facilitate the manipulation of the behavior of humans, either for advertising purposes or propaganda purposes. Now, advertising and propaganda are nothing new, but the sophistication with which our phones, with which other systems might be able to manipulate our behavior, this has not been seen in the past. And there are fundamental questions about who should have the right to manipulate our behavior in this way, let alone what is acceptable for the machines to do and what is unacceptable, and whether they can parse that out in real time when they're confronted with a new opportunity. There are adversarial attacks, and adversarial attacks are the capacity of those with bad intent to actually destroy the capacities of an existing learning system by just introducing new information into the data set upon which the system was trained that just undermines what it had already learned. So for example, even a simple system that could identify pictures of a cat from pictures of a dog might actually go crazy if you introduced hybrid pictures into the data set and no longer be able to even perform that simple task. So one set of concerns focuses on inherent biases and use of data. An example of that might be the use of deep learning algorithms in law enforcement, where, for example, facial recognition software, which has looked at a vast body of information about faces and then is able to sometimes match up the face of a particular individual, identify who they are. In law enforcement, that's very problematic because there's a high degree of false positives. There's a high number. And even if it can be reduced to only 5% or so, a 1 in 20 mistake is deeply problematic, particularly when some of the data may be biased. The other very big area of concern is the potential unpredictability of both complex adaptive systems and learning systems. So these are all complex adaptive systems, as are humans, as are societies, as are markets, and at times they can act in unpredictable ways. And also as learning systems, they are changing the processes by which they make decisions, or they see information upon which the decisions are based. And in that learning, they might take an action that was unanticipated, or they might have actually undermined the effectiveness of built-in restraints on the system itself. But unpredictable actions may only occasionally be problematic. Most unpredictable actions may be pretty insignificant. So when is an unpredictable action one that we need to be concerned about? Well, we need to be concerned about it when it carries a high risk. And even an action that takes place only occasionally, if it is high risk, if it can have a high impact, then it should be of concern. In other words, low probability situations that can have a large impact, for example, a lethal autonomous weapons that isn't just killing one individual on a battlefield, but could actually drop a bomb that could kill 10,000 people, even if that's a very low probability of occurring, that's a very high risk. The awareness of inherent biases, the inappropriate use of data in ways in which it could evade privacy or been used inappropriately to manipulate human behavior, and perhaps even low probability but high risk situations, all gave birth to a robust AI ethics movement. There have been individuals like myself who have, for example, been involved with AI ethics for 20 years now. But I'm talking about a robust AI ethics movement that now has tens of thousands of people focusing concerns on what can go wrong and how we can minimize the likelihood of what goes wrong. AI ethics has not only focused on privacy, fairness, and accountability, but it's also focused on the issue of transparency. One of the difficulties of these new learning algorithms is we don't know how they got from the input to the output they gave. And that's deeply problematic, particularly if something goes wrong on the output side. So consider a learning algorithm that leads to an accident with a self-driving car. At the least, we would like to have forensic transparency so that we could ensure that that accident does not reoccur. The AI ethics movement has given rise to an array of different lists of principles that should guide which systems we deploy and which systems we should not deploy, what kind of testing systems should have, to what extent we can design values into the systems themselves, And if we can't adequately attest them, if we can't adequately predict what they're doing, then how we ensure that they are not deployed in risky contexts. And these principles, they have informed work by the OECD, work by the UN and UNESCO. There are even lists of principles that have come out of China in the form of the Beijing principles. Generally, these principles are the same in nearly all contexts, but there are differences. For example, the China principles don't talk about the protection of human rights, but instead they talk about ensuring harmony. Within the AI research community, the advent of deep learning created not only deep excitement around the rapid progress that might be made in developing useful artificial intelligence, but also a lot of visionary enthusiasm around rapid progress that would take us toward the development of artificial general intelligence. AI systems like our heroine, who are capable of doing almost any human task and exceeding humans in some respect. But it also came along with questions about, well, what if we really succeed? Can we ensure that our artificial general intelligence or artificial superintelligence do not create safety concerns and even existential risks for the future of humanity? Before the advent of deep learning, research in the AI community largely functioned on just ensuring that the systems being built functioned to perform the tasks they were designed to perform. So how do you ensure that a system stops when you want it to stop? How do you ensure that systems such as those that many of you have seen from Boston Scientific can walk over rough terrain and maintain their balances? But with the advent of deep learning, AI researchers, like all other engineers before them, became much more concerned with AI safety, ensuring that these systems were safe, deployed appropriately, and made appropriate decisions. It's important here to note a distinction between the attitude of the AI researchers and the attitude within the machine ethics community. The machine ethics community had initially focused upon how do you even get an artificial intelligence or a computational system or a robot just to make appropriate decisions even in low-level risk situations. The AI research community was particularly focused on ensuring the safety of advanced artificial intelligence. Forms of artificial intelligence like those illustrated in the Spark Hunter file that are far from being realized today. Rather than focus on the bottom-up and top-down approaches that we've illustrated, they came up with a new approach that they called value alignment. How do you get an advanced system to align its values with those of humans? And an approach, a value alignment approach, was put forward. This value alignment approach suggested that these advanced systems should be able to deduce appropriate conduct by observing humans in the field, by observing human actions. But again, this confronts us with the ceiling ground problem. A lot of actions that humans take are not ethical at all. So who will they model their behavior on? The value alignment strategy posited that values can be learned by observing human behavior. In its initial conceptions, it discarded the language of normative ethics in favor of terms that were much more computationally tractable. Concepts such as utility functions, system goals, agent preferences, and value optimizers. But in discarding the language of normative ethics, it lost some of the nuances entailed in concepts such as justice, such as benevolence, such as duty and virtue. The conceptual tools of the value alignment approach, at least in its early iterations, carried no ethical import, carried no ethical significance. And it was particularly attracted by theories such as utilitarianism, which seemed to suggest ways of forging a mathematical approach for determining what is the best action, how you maximize the good for the most people. Unfortunately, in all of this, there's computational slippage. There's a loss of some of the texture and nuance of what we expect from good ethical decision makers. But more importantly, the machine learning algorithms we have today are not ready for the value alignment approach. They don't have the capacity to factor in mental states, subtle emotional rewards, relationships with others, and punishments, all of which play significant roles in the making of ethical decisions. So the bottom line is that higher order ethical thinking, the working through of complex problems, is much more difficult than we've hitherto understood. And the machine learning tools we have today are far from giving us adequate means to implement those kinds of decision-making capabilities.